Bio-G 1500 Professor Mark Savari enjoying his day off.
Knock, knock.
Come in.
Oh, sorry to interrupt you on your day off.
Lab TA Ethan Degner.
Oh, that's all right. I was just logging.
Okay, well, I was actually just wondering if you could explain a tiny part of basically the entire limiting nutrients lab. Kind of need to catch up a little bit.
Oh my. Well, let's make some breakfast first.
Wait, what are you doing? You don't have enough plates for 2 whole servings. You've only got enough for 1. You can't make 2 servings of toast with only 1 plate.
But I have so much bread.
Well, yeah, but you're going to round up plates before you use up the bread. Even if you've got 10 slices, you can still only have enough plates for 1 serving.
So you're saying that even with enough bread for 10 pieces of toast. So you're saying that even with enough bread for 10 pieces of toast and say enough butter for 40 pieces, we're going to run out of plates after the first serving?
Yeah, because even though we have so much bread and butter, we only still have enough plates for 1 serving. Therefore, the plate's limited.
That sounds familiar.
Well, I don't really see what bread has anything to do with limiting nutrients, so could you please get on with it?
And so Mark spent the rest of his existence trying to explain the limiting nutrients module.
So now we're going to hop into actually talking about limiting nutrients. And the first concept that I'm going to cover is the basic difference between primary and secondary, which I know you're all very familiar with. So primary is the nutrient that runs out first, which, as you can see in Liebig's barrel, is the shortest plank, and therefore the barrel can only be as full as the shortest plank, which represents obviously the growth of the organism. And the secondary is the second nutrient to run out after the first one has been refilled. But aside from breakfast catastrophes, why do we care about limiting nutrients? Well, as you can see here in Lake Erie, if a nutrient has been put into the body of water and it's extremely limiting, then the algae can overtake, and this drags lots of oxygen out of the water and can create dead zones, which are very difficult to reverse.
And the 2 limiting nutrient experiments that we did were ones with the effect of a certain nutrient on algal growth. And for algal growth, it could either be on a single species like Chlamydomonas ranhardi or Ancistrodesmus falcatus. And in the second experiment, we looked at the interaction between 2 different species in the presence of added nutrients. And the whole purpose of both these experiments were to determine whether or not added nutrients affects growth, and if it affects growth differently for different species of algae.
So an important takeaway from this lab was the tools that we learned how to use. And we'll just go over that real quickly with the practical coming up this week that I'm sure everyone is excited for. So first there's the spectrophotometer, which is used to measure absorbance. The way this works is that it projects light through a cuvette containing liquid. A thicker liquid, i.e. in our case a liquid containing more cells, will absorb more light, and thus less light will get through to be measured. So use the spectrophotometer. First a blank cuvette is inserted containing only distilled water. This is used to zero the spectrophotometer, and then a cuvette containing the sample we actually want to measure is inserted. You can set it to scan for multiple wavelengths, and you get a graph that looks something like that. This person was measuring the absorbance of beta carotene. We could be measuring the absorbance of whatever. Select the highest peak, which in this case is that really high one around the wavelength of 40 nanometers, and take the absorbance of that. And from that and the cell density, you can find the conversion factor, which I'll explain in just a moment. Can't find the cell density with just the photospectrometer though, so real quick, just go over how to use a hemocytometer again. We've been over it several times, so I'll make it quick. Use a pipette to take some of your sample, put it on the center of the hemocytometer, and then zoom in onto this grid using the microscope. You can zoom in onto the squares highlighted there, and you're going to count the cells in 5 of them, 4 corners and 1 from the center. If a cell is on the edge, in order to avoid overcounting, you ignore cells that are on the right edge, the bottom edge and the two right corners, and only count cells that are on the left edge, top edge, and two left corners. You take the average count for those five squares that you counted and divide that by 0.00625 to convert it to units of cells per microliter. Now to get back to the conversion factor, let's say we have two samples, sample A and sample B, and from the spectrophotometer, we know that sample A has an absorbance of 80, and from the hemocytometer, we know that has a cell density of 500 cells per microliter. So find the conversion factor, 500 divided by 80, we get 6.25. So now we have sample B, we put it in the photospectrometer, and from that we see that it has an absorbance of 60, but for whatever reason, maybe lab's almost over, we don't have time to use the hemocytometer. No problem, use the conversion factor, 60 times 6.25, and we get 375 cells per microliter. It's faster and it's more efficient. Hey, good luck on practicals, everyone.